Hello and welcome back to Calculus 1. Eventually you will be able to do it the same pace tonight. But, all right, so chain rule. This is going to be probably, well, not probably, definitely the most used derivative technique. Most of the time, you don't see functions in their natural state. You would see maybe x squared, x cubed, sure. Sine x here and there. But more often, you're going to see sine 3x, sine x squared, sine squared x. You're going to see e to the x squared. You're going to see function composition, and then you have to take derivative of that. So chain rule is designed to deal with the derivatives of composite functions. And those problems are most of the time, when you take derivative, it's one of those. So it is going to be the difference between taking the derivative of, as I said, e to the x and taking the derivative of e to the x squared, right? So you see that the function that it's on x, the function that is on e, is now more complicated. You can also deal with e to the sine x, and technically anything that is thrown at you, you can do it. Further, chain rule can be combined with product rule, quotient rule, so we are going to have those types. And then, as always, we are going to say find the equation of the tangent line and give you a function for which you will have to use chain rule to solve. So what is the formula for chain rule? How does it work? Why does it work? And so we start from writing down that the derivative of function composition is the outer function, derivative of the outer function with the inner function still plugged in, times the derivative of the inner function. So this is the standard way to write the chain rule formula. And there are other ways to write this as well. Note that f of g of x is the function composition, and function composition in a sense that g is plugged into f. Now, this is one of the major sections in your pre-calculus class, and if you don't understand function composition, well, then probably this section and the rest of your calculus career is going to be difficult until you figure that out. So what is the function composition? Function composition is when you plug one function into another function. That's what it is. So you're not adding them, multiplying them, you are plugging one function into another function. You know that your wallet has the function to hold money and cards and stuff, right? And the bag has function to carry stuff. So you can put the wallet in the bag. If you need a visual representation of what that is, you plug one function into another function. So bag and wallet have separate functions, different functions. Your book has a function to give you knowledge, right, if you want to read it. So you put book into the book bag, right? So you can nest. And then, guys, you can chain as many of these function compositions as you need to, because that wallet is going to go into the bag, and then bag is going to go into the car, and the car is going to go into the garage, right? So there's a lot of, and each one of those next layers is a function of a different kind. So I can have g of x in f of x, which is in h of x, which is in k of x, which is in w of x. I can chain as many of these as I want. So the process over here, the idea is that if you think about this in terms of what's happening, we are going to take the derivative of function, well, the derivative of f in respect to x is the derivative of f in respect to g times the derivative of g in respect to x. And I hope that you see that when you cancel these two, you get df over dx is the df over dx, right? So This piece over here is called the chain, the one that takes you to the next, the one that takes you to the closer to your independent variable. So I'm going to give you a few examples of this, and the first example is, as I said, e to the x. That could be very simple. Let's do sine actually. So the derivative of sine of x squared. So if you are observing the formula, you are supposed to figure out which function is the outer function, the main function, and then which function is plugged inside. So looking at this, which function is the outer and which one is the inner? Sine x is outer, and then x squared is plugged inside. Now to understand that, I'm going to say that the function composition works this way. F of x is sine x, and g of x is x squared. So this one gets plugged in there, and you get sine x squared. So now, when you are dealing with the derivative, you are supposed to take the derivative of the outer function. You know the derivative of sine is cosine, but you are to leave the g plugged in. So you took the derivative of the function as is, but instead of placing an x, you have to place whatever it is. Now, I'm going to actually show that in symbol soon. Now, times the derivative of the inner function, which is 2x. So you are going to write 2x cosine x squared as the final answer for this derivative. Now I am going to do the same problem in general terms of figure out what is the derivative of sine of g of x. See, I am not going to use specific x squared now. I'm going to say in general, because that x squared could be x squared, but it could be also anything else under the sun. Could be logarithm, could be, right? So the idea over here is that the derivative of sine is cosine of g of x times the derivative of whatever that g of x is. So that's what's happening here. And if I want to use the same formula on the basic formula, sine, just sine x, well, the derivative of sine is cosine, right? And we copy this, and then times 1, right? Because the derivative of x is 1. So that's why we don't write it, and it's just the derivative of sine x is cosine x. So for any one of these, when you are replacing the original x that was in your original basic form with g of x, you have to follow with what we call the chain, which is the derivative of that particular function. Let's take a look at another example. I'm going to say, first I'm going to ask you, what is the derivative of square root of x? Yes, you memorize this one. You memorize this one because it's very frequent, and instead of going and writing the 1/2 exponent, drop 1/2 down, 1/2 minus 1 is negative 1/2 to get all of that stuff, just bite the bullet and say the derivative of root x is 1 over 2 root x. You're memorizing that one, and because it's very frequent. It's very frequent. Calc 2, Calc 3, all gonna have it. Now, I want you to visually see this. I'm replacing x with sine x. The form of the derivative must be identical, and then times the derivative of whatever else I have instead of x under the root. I'll do one more example with the square root again. And then times now, for me, this is the same problem all the time, right? Because, look, it's the same structure. Every time it's the same structure for the problem. Is that the chain over here, there is a times 1 because the derivative of x is 1. But I don't have to write it. And then derivative of sine is cosine, derivative of this polynomial is that polynomial there. Do we see this? See how it works? So chain rule is designed to deal with function composition, derivatives of function composition. And if you study these examples in this fashion, should be okay. Now I'm going to ask you for input. What's the main function here? What's the main function? X cubed. Very good. X cubed is the main. So this is that pre-calculus prerequisite that if you don't know, this section is going to be a living nightmare. And then the rest of the calculus. You have to see, you look at this and you say, the main shape of the entire problem is x cubed. Something cubed. So that's the shape, and the derivative of that is 3 blah squared, right? This could be sine x, it could be cosine x, it could be ln x, it could be whatever there, right? The shape of the entire problem is something cubed, whose derivative is 3 something squared, and then the chain rule is the derivative of the inside, which I call guts, derivative of the guts. So the outer function f is x cubed, the inner function g is x squared plus x minus 1. Therefore, the derivative of this must be 3 whatever squared, and the whatever was x squared plus x minus 1, times the derivative of the inside, which is 2x plus 1. When you're taking the derivative of polynomial, right? 3 minus 1. Now, if you are still struggling, you can go and say, all right, so if I just briefly in the margin of the exam or the homework paper, if I briefly just replace this with the g cubed, right? G of x cubed, then we know it's a 3g of x squared times g prime. Can you see that? Yeah. Right? It is impossible to learn this problem by problem because infinitely many combinations of functions and what goes in exponent and what goes, right? So, and then when we, add to this product rule and quotient rule on top of everything, then it just becomes really crazy thing. So some function g cubed. Well, what is the derivative of x cubed? It's 3x squared. So what's the derivative of g cubed? It's 3g squared, right? You have to see that this is the same thing, except now it's applied on a function. So observe that it's a cut and paste, right? Control C, Control V over here, because that's the g part, and g was this mess. And then times the derivative of g, derivative of x squared is 2x, derivative of x is 1. Now the only thing that I really don't like is teaching this on Thursday on a summer course, because if you don't do this tomorrow, it's going to evaporate and it's going to be hell on earth starting Monday, because the rest of the course and the rest of your calculus depends on this particular lecture. This is going to be the derivative that you're going to be taking 95% of the time. And then product rule and everything else is going to be 5%. So you must know this. Let's see, how about if I say, what is the derivative of cosine cubed x? What is the main function? What is the yes? Beautiful. It's still this. It's the same problem. I just asked you the same problem. Cosine x cubed would be a different problem, because then x cubed is plugged into cosine, but the cube is on cosine. This problem looks the same as this. So, exactly, 3 cosine squared x times the derivative of cosine is negative sine. And now I want to contrast this with this one. The placement of the 3 is very important. You can't just put it anywhere. So try that one on the bottom. Clearly cannot be the same as the one on top. So what is the main function? Cosine is the main function. What is the derivative of cosine? So it's going to be negative sine, and we copy the guts, which is, right, x cubed, and then times the derivative, which is 3x squared. So, and we write it nicely then. Good. I would like you to solve this problem in 2 different ways. And make sure you get the same answer. Use the chain rule, and also FOIL first, and then use the basic derivatives, right? Because if you FOIL, you will be able to use basic derivatives. So on a problem like that, you can use either. You can go from an hour to a day.
I think it's the generation you want to understand.
So where do we start? What should I write first? So let's go. Way one is do the chain rule. What should I write for chain rule? And then times the derivative of the inside, which is just 1, right? So who cares? So we're getting 2x plus 18, right? Okay, way 2. We FOIL. And then when we take the derivative, what do we get? So you see that in some cases, right, you can use the old. But what are you going to do when this says 200, right? Are you actually going to FOIL? And the answer, hell no, right? Then in that case, chain rule becomes a must.
Most of the time you use the chain rule.
What happened?
Most of the time it's beneficial, like the chain rule.
95% of the time of any derivative in any course ever taken. This is technically the derivative of g squared. Something that is squared is 2g times g prime, right? Nope. X plus 9 is plugged into x squared. So you say, guys, guys, this is x squared, right? So x squared. So that's why I called it g squared, because x plus 9 is g. So what's the derivative of x squared? It's 2x. What's the derivative of g squared? It's 2g times g prime. That's the chain rule, introduces times g prime. So here's your, over here, 2x, right, which is 2g, times the derivative of the inside is 1. Yeah. Yeah, you're next. No, but now I have to apparently.
I feel like sometimes you would just put a plug on that. Moving on.
Let's go and take a look at exercises from the textbook. It's whatever they have. And they love these kind of stuff. What's the derivative of tangent 5x squared?
Wait, Professor, what was that way you told me to memorize the... You told me a way. Like if it's negative, it's going to have like top, you said, something like that?
Mm-hmm.
Oh, yeah.
and then times the derivative of it? Is that
cosecant squared 5x squared.
alright? Yeah. So the derivative of tangent 5x squared is secant. So would I do secant 5x squared times the derivative?
Secant squared. Yeah, and times the derivative.
Okay. So use secant squared first? Okay.
So which is the outer function? Tangent. So what's the derivative of tangent? Secant squared. So we start with secant squared 5x squared times the derivative of the inner function 5x squared is 10x. And then we write it nicely. Nice. The next one is e to the square root of x.
Like you need something like with some longer range, you know? Like one of those squirt guns in the water.
Ready.
Yeah.
Is this like Russian roulette?
Exactly.
Wait, so what do you do?
This is what my mom does to our cat. You never do that?
Nah. My animals are well behaved, so they don't get squirted.
Which means they're not fun. Which means they're not fun. All right, so what do I write here? What's the main function? E to the x. So what is the derivative of e to the x? So I write root x. And then times? Yes. So it's e to the root x over 2 root x, right? Nice. So that was problem 14. All right, went back. Next problem is, oh, by the way, in the book, and they give you version 1, version 2, chain rule, and so on. It just doesn't. Just do it. 22. The derivative of the square root of x squared plus 9. What's the main function? Square root of x.
Yeah, let's go.
So what is the main function? Square root of x. Good. So we start with 1 over 2 square root, right? And it's x squared plus 9. Happen to be x squared plus 9. So the form for the derivative of a square root is 1 over 2 square root. Whatever was under the root stays under the root. And then times the derivative, which is 2x. And now 2 and 2 will cancel. So we're going to have x divided by the square root of x squared plus 9. Are we all clear on this? Next example from the textbook. Let's see some other stuff. Ooh. No, this is a really interesting thing. I'm right with you there. The derivative of sine of 2 root x. What is the main function? What's the main function? Sine of x, whose derivative is? So it's cosine, and we copy the inner function, and then times its derivative, which is? And there it is.
So, how do you know that?
Can we cancel root x?
Hell
Hell no. All right. You ever seen this proof before?
Oh yeah.
You've seen that? What's the trick to this proof? What is it?
Cancel the end.
You cancel the n, exactly.
Wow. So good.
I shouldn't have been as funny as this.
What are you up to?
Shut up.
Very good, look.
I'll do this one more. My dad was.
Anytime you have someone who's way too smart for your liking, ask them to prove this to you.
Wait, I gotta take a picture of that. Make sure.
That's how it's done. All right, and let's see the next example, because there is just so many and they're all wonderful. Oh, you already know.
Yeah. Because it does go on forever.
All right.
So,
Welcome to the next level.
so now this is gonna be cosine. Wait, cosine squared x cubed.
What happened?
Cosine squared x cubed.
Nope.
What are we doing?
How many functions do we have on a pile? 3 functions. Very good.
Yeah.
That means the main function, and then the inner function, and then the most inner function. Think of it as layers of onion. Have you ever seen onion? I don't know if you cook or not, but I did today twice already. So yeah, breakfast and what I call dinner at 3. So it's like layers of onion. So you have the outer function, which is the outer shell, and what's the most outer function for this problem? X squared. Very good. X squared.
I'm not grasping that.
And then what's the one layer in? Sine x. And what's the one all the way on the bottom? X cubed. Now look at this. Guys, this is all experience. Some of you are better than others at this point in class, at this stage. That doesn't mean that the rest of you can't catch up if you actually put the honors effort over the weekend. This is simply the Calculus 1 prerequisite for this section. If you're having trouble, you don't know that particular part of pre-calc. That means you are going to find either my lecture on a YouTube channel from Calculus1 on composition, function composition, or someone else's, or you're going to pick up the book, because you have to be able to mentally decompose the function so that you can change the derivatives in a proper order. What helps here? It helps if you know order of operations, obviously, but it helps when you know that sine squared x is the same thing as sine x everything squared, which is different than sine x squared, because this one entails x times x, and this one entails sine times sine. Those are 2 very different creatures, and you're going to have this down the line with ln as well. Ln squared x or ln x squared. So when I rewrite the problem and I have this square here extracted on the side, and then this thingy is cubed, you can see that the entire problem is cubed, which makes squared, which means that the entire problem is x squared is the most outer main function. And then you dig deeper, and the next layer is sine, and then the next layer is x cubed. Do we see that?
Yeah.
So now let's change the derivatives. Did I answer your question?
Yeah.
Good. So the next is, what is the derivative? It is 2 times, right? This 2 drops in front, power rule. 2 times sine x cubed times the cosine of x cubed times 3x squared. Now observe the chain here. Here is your 2, everything else to the first power, times the derivative of sine is cosine, times the derivative of x cubed is 3x squared. So it's going to take time, but again, and another thing that just motivational piece, guys, whenever this thing looks it's so hard and then inapproachable and so on, just realize that in this school, you are the top 2% we have at RDCC. This class right here. Out of 8,000 students, we have 4 classes, 4 sections of 5 sections of Calc 1. That's equivalent to 2%. You are sitting in 2%. When you go to NJIT, you are 100%, okay? But here, you are 2%. And you're 2% for a reason. You are at that level. They're operating at that level. The others are not. And then the Calc 2, you are 1%. And the Calc 3 and differential equations, you are 0.5%. There's a reason for that. So you have to understand that you are operating now at this level, and when the stuff is hard, imagine how it's for those who are not even there. So extra work. There is no it's extra work. When you stumble, you get up, you pick up, and always pick up at prerequisites. If I go around the classroom and ask what's the derivative of x cubed, you know it. What's the derivative? That's the calculus piece. if you are getting tripped right now and you have no clue what the hell is going on, it's not calculus. I promise you it's not calculus is tripping you here. It is that prerequisite that you are not able to mentally decompose function composition and you don't know in which order you are supposed to take derivatives. That is what's tripping you, and that's pre-calc 1. And for years I'm saying no one fails calc 1. Students fail two things in calc 1, algebra and pre-calc 1. That's what you fail in calc 1. In calc 2, you fail, again, algebra, limits, and calc 2 trig functions. That's what you fail in calc 2. So no one fails calc 1, no one fails calc 2. But whoever fails the class fails heavily on a prerequisite. There's no way that you will convince me that you are sitting in a calc 1 class unable to memorize a formula. There's no way in hell you would get this far. So you have mental ability. It is just you forgot this building block which prevents you from pushing forward. That means your job tomorrow is to spend an hour or 2 hours learning the pre-calc 1 concept and then spending 15 minutes to finish off this chapter, this section. That's how it goes. Or you can waste 7 hours trying to figure this out without figuring out the basic building block. There's just nothing you can do. So that's the part of how you get to be successful in these exercises. Next problem is, holy nightmare. All right. No, you got this. This is the problem from the textbook, so, you know, all the hate mail and everything goes to the address provided in the textbook. It says sine squared of e to the 3x plus 1.
You want me to picture it as for the last one? Look at this first, the middle, like in the center. This will be x squared and sine x and then x cubed.
Yeah, but it's not at the center. It is that the sine.
I used to be really good at composition. Yeah.
Sine x. Well, it looks like this, right? You can rewrite it that way, and you can see that the square is the boss for everything.
Gotcha.
And then sine is inside, and x cubed is inside further.
Wow, that's a lot easier.
Well,
All right, thank you.
If you are having issues, try to write this first, right? The list of what goes where. What's on the top? What's the most? X squared. Dig deeper. What do we get? Dig deeper. Dig deeper. 4 of them, right? 4 of them. Do you also see that these two are nearly the same problem? Sine squared, sine squared? It has to start the same way. What's the derivative of x squared? 2x. So now this square goes and starts 2 sine of e 3x plus 1. Great. Now what? Times cosine. Very good. Derivative of sine, which is the next level down. Derivative of sine is cosine, and you copy everything that is inside. And then next level. Derivative of e. What's the derivative of e? E. So that remains the same. And then times? Yes. Derivative of 3x plus 1 is just 3. And now depending on, you know, the level of skill that you have, you might notice that this is the double angle formula from pre-calc. So you have 3e 3x plus 1 sine 2e to the 3x plus 1, which condenses the most. But wait, we can make it more annoying. There are also problems in their 60s, yes.
What's the most number of layers that's going to be on the exam?
Depends on the current mood. No, I actually never had a 6. The most I believe I ever had was something like a 4, but then I would say 3 is the standard, and then it might be a 4th layer, but 3 is the standard. What happened?
As you grip the water bottle threateningly.
All right. Well, oh, there it is. All right, ready?
Yep.
No.
What happened?
Is that it?
What, disappointed? I can make it worse.
What X cubed?
What's happening here?
Payroll product.
What's the main thing that is happening here?
Product.
Product rule.
Yeah, but X cube's the outer, right?
No, x cube is on its own. So do we all see the product rule? There is a function x cubed that it's multiplying another function, right? Now do we also see chain rule in this one? Because there is one function buried into another. So this over here is a basic function. There's no chain rule there. That's a basic function. The second one is the chain rule where you have x to the 4th on top and secant buried inside. So this is the product rule. With chain rule within. So when I have to take derivative of the second, that's when the chain rule kicks in. So copy the first times derivative of the second. So what's the derivative here? 4 secant cubed x, right? Because the outer is x to the 4th, so it should be 4x to the 3. And then times, what's the chain? What's the derivative of secant, the inner function? Exactly. And now we get plus, copy the second, times the derivative of the first. So there's your product rule right there.
Are you missing a 3 at the x, at the very first x?
Yes. Cube. Copy the first derivative. Sometimes actually the software just disregards things. Great. So now put everything together. We have 4x cubed secant to the 4th x tangent x plus 3x squared secant to the 4th x. What can I factor? Good. And what's left? We want to get used to factoring as soon as possible because chapter 4, that's just the first step. In chapter 4, I'm going to say, graph this function by hand. That entails you taking the derivative, setting it equal to 0 to find min and a max points, right? So now, each one of these gets set to 0, and you find, right, clearly you have a 1 and 0, and then, right, top one later. That's happening in 2 weeks, guys.
Wait, no, it doesn't.
Yeah, it does. With or without you. I mean, if you say no, it doesn't, I'm just promising you it does. If anything happens to me, someone else is taking over the course. So it's happening in 2 weeks. I'm telling you that 100%, regardless who's missing in the classroom. Unless you all drop. If you all drop, then it's not happening. That's the only way how it's not going to happen. But if some of you are not here, if I'm not here, it still is going to go on. You know how to say the show must go on? That's that. You're going to love this one. What's happening here? A quotient rule, exactly. Now, which one is the main method? Is the quotient rule main method or the chain rule main method? Chain rule is the main, and quotient is built in. Now, previous, what was main method? Product or chain? Product, right? So this time, chain is the main. So you have to kind of figure out, you know, what's going on. So I'm just going to write over here. If the problem looks like this, let's say, then the quotient rule is the main and chain rule is buried in. So you have to practice composition. You have to be 100% clear with composition. All right, let's do this one, and you'll have a wonderful 4 days of homework for chain rules so that you can become experts. And as I said, guys, most of your derivatives later on are going to be chain rule, 95% if not more. And here and there you're going to run into derivative of sine or derivative of x cubed or something like that. Because the world is not that boring. It's modeled by more complicated functions. So what's the outer function? What's the outer function? X to the 8. So outer function is x to the 8, and the inner function is quotient. So 8 blah to the 7th. That's how we start. Right? Times the quotient. Fill in the blanks. I strongly encourage you to come up with your own examples. Just chain these functions in any way you can. Do the problem, and then fire up Mathematica or Simulab online or Wolfram Alpha and check the problem you made up. The goal is to do 100 of these problems over 4 days. It's only 25 a day. That's a goal. It builds a character.
Go outside and dig a bunch of holes. That's what I got the dirt from. Go out in the desert and dig a bunch of holes.
So we have when we factor, we have 8 e to the x over x plus 1. So probably the algebra is the worst for this problem. We pick out e to the x, and we are left with x plus 1 minus 1, which is just x, divided by x plus 1 squared. Now notice that there's e to the x, and then another e to the x, and then there's x plus 1, and then x plus 1 again. We can combine them all. So in the numerator, we're going to have 8 e to the 8x times x. So 8x e to the 8x. And in the denominator, we have x plus 1 to the 9th power, because you have 7 here and 2 here. That's altogether 9. So that's the simplified version. And then when you say equal to 0, the denominator dies. 8 doesn't contribute. This one has no solution, so just x equals 0. Very simple.
Is it a 9 or a 2 in the bottom?
2 plus 7 is? You see that this one has 7?
Oh, so you add them?
And then this is 2, right? So put them all together. Great! Off you go to do tons of homework and labs and stuff. See you on Monday, 4 o'clock, 4:30.